This video is going to try and show you how to convert a definite integral into the sigma notation of a Riemann sum, which is one of the trickier things we've done so far. In order to do that, you really have to understand what a definite integral is and how a Riemann sum tries to simulate that. A definite integral is the product of a y value times an x value. That's what this notation means. It's the product of this y value times this x distance, I should say. Y value times x distance. The only problem is the y value is changing. If it were just a constant y value, like if it was y equals 7 or something like that, finding the product of the y value times the x distance would be easy. You just multiply one number times another. But in a definite integral, the problem is that the y value is changing, so we don't really know exactly how to multiply a changing number by an x distance. So what the Riemann sum comes along and does and says, all right, well, let's just pick one y value at a time. So maybe pick this y value and multiply that y value times the x distance, and then pick another one and multiply that y value times the x distance, and then we'll do it one more time. And so instead of saying, all right, my y value is changing, I don't know how to multiply it, I'm just going to pick 3 y values from the course of that function and multiply each of those 3 y values. So we'll call that, call the first one f of x1, and then f of x2, and then f of x3. Those are the 3 y values. Sorry that got a little bit messy. That we're multiplying by. And each one of them is going to be multiplied by the x distance in each case. So maybe it'll be neater if I write it here. F of x1 times dx. And then f of x2 times dx. And then f of x3 times dx. If we add those 3 things together, remember, for each one, the product is the multiplication, the length times the width of a rectangle. So that's why we think of it as areas of a rectangle. But really, we're just talking about the product of 2 numbers. And it's worth pointing out that there's no rule that says that all of these 3 dx's need to be the same thing. One of them could certainly be wider than the others. If you want to show it in here, you can label that as dx1, dx2, and dx3. That's if your widths change throughout the process. For our purposes, I think it's a little bit simpler if we pretend that they're all just going to be the same. That's a little bit easier. So in order to turn that into a sigma notation, we certainly could write it as the sum from n equals 1. I shouldn't say n, that would be confusing. I'll call it k equals 1 to 3 of the f of x sub k. And what this k here means is it's what's going to rotate or escalate the first one, the second one, the third one. This index of summation down here, this is what we're saying is going to be increasing as we go through the sigma notation, through the sum. Every time we add another product, that k is going to go up by 1 times dx. But the problem with this, and this is just the general idea of a sigma notation, and of course if we wanted to, we could replace that 3 with a more abstract n if we wanted it to be some bigger number of rectangles. The problem with this is that you can't really evaluate this. You can't really plug that into Desmos and know what to do because the x values have to be selected. So what we want to do, the trick to writing the sigma notation, is to turn this x value that's being plugged into the sigma notation, recognize the pattern in the x values that we chose here, right? This was x1, this was x2, this one was x3. Recognize the pattern in those numbers so we could describe it in the sigma notation. So that's what you have to do. And the truth is, we can make it kind of be an easy formula. Okay, so the key is, and this is for a right sum, all you have to remember is that the three x values we used, 1, 2, 3, are each the same distance away from the last one. And we can figure out what that distance is. The width of each rectangle is the total distance of our interval from B to A divided by however many rectangles I want. That's what each of those distances is. Again, assuming we're keeping them constant. So the first x value here is that very distance, that dx, above our starting point of A. So we can call that A plus, I'm going to say 1 dx, or just A plus dx. So that's what this x value is here. It's A plus 1 dx. Now, it's a little bit weird to put that 1 in there, but maybe you've guessed that the reason I wanted to call it 1 dx is that the next x value we're going to use is going to be A plus 2 of those steps, A plus 2 dx. Since each step is the same width, this position right here is 2 of those steps above the A that we started from. So this is A plus 2 dx. And of course, this last one here would be A plus 3 dx. And so if we say it that way, we can put that into the sigma notation by recognizing that those three numbers, the 1, the 2, the 3, that's going to be the k that just keeps going up, starting from k equals 1 up until whatever n is. Remember, it doesn't have to be 3. It could be a much bigger number. So it's going to be f of a plus, this is the spot where the k goes. So in my sigma notation, I'm just going to call that k times dx. And if you can remember this, you're in pretty good shape. Let's give you an example. Let's say f of x was equal to the square root of, let's just keep it simple and call it x. Let's call it x plus 2. And I want the definite integral, let's say from 4 to 9 of f of x dx. So I'll even write square root of x plus 2 dx. So we're going to use this as our guide to turn that into a sigma notation. It can be approximated by the sum from k equals 1 to n. Remember, that's just saying we're going to need to go starting from 1, and we're going to keep going. For as many rectangles as I want, I'm going to keep going. And that number of rectangles is just n. The square root, because this is where I'm going to put in my f of a plus k dx. That a plus k dx is taking the space of this x value right here. So I'm going to take that x value and replace it with a, which is 4, plus k times dx. And I'm sorry, I meant to figure out the dx first. The dx is 9 minus 4 over n, which in this case is 5 over n. So that's my f of a plus k dx. Oh, I'm sorry, almost. Don't forget there's a plus 2 there. So there's my f of a plus k dx times dx, which is the same 5 over n. And might as well touch up that last one little thing, which is the 4 and the 2. I can combine them together. So that's 6 plus 5k over n times 5 over n. And that's the sigma notation. Now, it's important to point out that this was for a right-hand sum. If it was a left-hand sum, it would be completely different. That's actually not true at all. It would be only a tiny, tiny, tiny little bit different. What would be different if it was a right-hand sum, if it was a left-hand sum, I'm going to borrow this, bring it down here, is if it was a left-hand sum, then all that would change is instead of using a plus 1 dx as my first spot, I would actually use a itself to make my first rectangle, or my first product, I should call it. And then my next one would be a plus 1 dx. And my third one would be a plus 2 dx. So notice how even though I'm adding up 3 products, the k's that I have here, well, this is 0 dx, this is 1 dx, and this is 2 dx. So the only thing that will change to make it a left-hand sum instead of a right-hand sum is that instead of plugging in starting with 1 where the k is and going all the way up until n, which is what we did in the first example, we started with 1, then 2, then 3, and we would keep going if we wanted more rectangles. For a left-hand sum, we're actually going to start at 0 and end not all the way at, so my k is going to be starting at 0, and we're going to go all the way up until k is not the number of products that I have, so not the number of subintervals, but, sorry, that got messy, but 1 fewer. Or n minus 1, that is 1 fewer subinterval, or the number is 1 smaller than the number of subintervals. So the only thing that will change is instead of going from k equals 0 to 1 to n, I'm going to go k equals 1 to n minus 1. That way, sorry, from 0, apologize for confusing that one. I'm going to start at k equals 0. That's my first k. And I'm going to go not all the way up until n, but 1 less than that. But everything else is the same. It's still f of a plus k dx times dx. So for the example where we had, it would be starting from k equals 0 to n minus 1 of the square root of a plus and the interval was from 4 to 9, so that b minus a is still 5, so the dx is still 5 over n. Times dx. So the only thing that changed, again, I'm going to put the 4 and 2 together again. The only thing that changed is instead of starting at 0 for k, so instead of starting at 1 for k, we're now going to start at 0. And instead of going up until the number of rectangles, we're going to stop 1 before that.